I am Nabil Hami, and I will start our presentation by sharing the abstract and introduction of our project. Our project is about detecting guns in media using the YOLOv10 deep learning model. Gun detection is a very high-stakes task because the presence of a firearm in public or digital space can instantly escalate into a serious threat to safety. Our aim was to create a system that is both accurate and fast enough to work in real-time environments such as surveillance cameras, public space monitoring, and even online content moderation. By fine-tuning the YOLOv10 model on a specialized gun dataset, we were able to balance high accuracy with the real-time inference speed, which makes our system a strong candidate for practical deployment. Now, moving on to the introduction. Gun violence is unfortunately a major issue worldwide. For example, in the United States alone, more than 48,000 people died from firearm-related incidents in 2021. Active shooter incidents are also increasing every year. These numbers highlight the urgent need for systems that can detect weapons quickly and reliably. The challenge is that in real-world environments, detection is not simple. There are many difficulties such as sudden lighting changes, occlusion when a gun is partially hidden, or crowded background, or even low-quality video streams. On top of that, in digital media, platforms like YouTube have to remove hundreds of thousands of videos every quarter that contain dangerous content, including guns. Doing this manually is not only slow but also stressful for human moderators. This is where artificial intelligence, also known as AI and deep learning, can play a major role. We framed our work as an anomaly detection problem, with guns being the high risk anomaly. By using YOLOv10, which is well known for being both fast and accurate, we wanted to show that real time firearm detection is possible and reliable. With that, I will now give my floor to my teammate Sabbir, who will explain our literature review, methodology, and evaluation metrics. Thank you.
Thank you, Nabil, for giving me the floor. Hello, everyone. I am Sabbir Ahmad, and I will be presenting the literature review, methodology, and evaluation metrics of our project. In our literature review, we focused on how researchers have approached the problem of anomaly detection and, more specifically, gun detection in media. One of the most significant contributions in this field is the UCF crime dataset, introduced by Sultani and his team. This dataset introduced about 1,900 unedited surveillance videos, making it one of the largest collections for anomaly detection. What made it special was that it covered 13 different types of anomalies, such as burglary, fighting, and robbery. The researchers proposed a method called multiple instance learning, which only required video level instead of frame level levels. This made it easier to train models on large scale data. However, the drawback was that the features they used were computational heavy, and the models struggled when videos were recorded in poor lighting or when objects were partially hidden. Another approach came from Leo and colleagues, who introduced the idea of future frame prediction. Their logic was simple but powerful. Normal activities are predictable, but anomalies are not. For example, if you were watching someone walk down a street, the model should easily predict the next frame. But if suddenly a gun appears, the prediction fails. They used generative adversarial networks or gangs to predict the next frame and then compared it with the actual frame. A big difference meant something unusual had happened. This method did improve accuracy, but it was very computationally expensive because gang training and optical flow calculations are resource hungry. So again, it wasn't suitable for real-time use. Finally, more recent research has explored YOLO-based systems. YOLO, which stands for You Only Look Once, is well known for being extremely fast while still accurate. For example, one study applied YOLO for anomaly detection and achieved high accuracy with very few latency, meaning the system could work in real time. However, many of these work didn't provide enough detail about the datasets or evaluation metrics they used, which makes direct comparison and reproducibility a challenge. So, from this review, we identified three main lessons. First, having large and realistic dataset is absolutely necessary to train models that can generalize to real-world situations. Second, anomalies should be treated as unpredictable events, which means models must be flexible enough to adapt to sudden change. And third, there need to be a strong balance between speed and accuracy. Because in applications like surveillance, a system that is accurate but slow is not useful, and a system that is fast but unreliable is also not practical. So now moving on to our methodology. For our work, we used the Kaggle dataset called labeled guns data for object detection. This dataset contains around 3000 images of firearms, each annotated with bounding box in YOLO format. The image include a variety of scenarios, different backgrounds, positions, and size of guns, which helped improve the generalization ability of our model. We divided the dataset into two parts, 85% for training and 15% for validation. Before training, we applied a number of pre-processing steps. For example, we make sure that all images were in the same format and resolution. We also organized the data into YOLO's required folder structure, which separates image and labels for training and validation. To improve model robustness, we applied data augmentation. This includes horizontal flips, random scaling, and mosaic augmentation, which essentially combines multiple images into one. These augmentations helped the model see guns in varied positions and context, making it less likely to overfit to the training data. For our model, we chose YOLOv10b, which is one of the latest version of YOLO and provides a very good balance between interface speed and accuracy. We started from a model pre-trained on the COCO dataset, which already contains a wide variety of objects, and then fine-tuned it on our gun dataset. Our training setup was as follows. We trained for 35 epochs with an image of 65 by 640 by 640, batch size is 16, and we used AdamW optimizer, and the learning rate is 0.01 default, and it is by default from YOLOv10b. And the loss function we used was a multitask loss that combined bounding box regression, classification loss, and distribution focal loss. In simpler terms, this means the model wasn't just learning to say whether an object was a gun, but also learning how to precisely draw the box around it with high confidence. So now let me explain how we evaluated the performance on our system. We mainly focused on three main metrics: precision, recall, and MAP, which stands for mean average precision. Precision measures how many of the predicted guns were accurately correct. For example, if the model detected 100 objects as a gun and 93 of them were correct, the precision would be 93%. Recall measures how many actual guns in the dataset were detected. For instance, if there were 100 guns in the dataset and the model found 90 of them, then recall is 90%. MAP is more complete measure that combines both detection and localization accuracy. We evaluated MAP at IOU threshold 0.5, which is a standard benchmark, as well as across multiple thresholds from 0.5 to 0.95, which is stricter. In addition to these metrics, we also analyzed confusion metrics to see where the model made mistakes, precision recall curves to visualize the trade-off between the two, and loss curves to monitor how well the model was learning during training. These evaluations gave us a detailed understanding of our model's strength and weakness before moving on our final result and analysis. That concludes my part. Now I will hand over the floor to my teammate Tasrif, who will explain the results, analysis, and conclusion of our project. Thank you.
Thank you, Sabbir. Hello everyone, I am Tasrif Ahmed Mohsin and I will present the results, analysis and conclusion of our work. About results, our YOLOv10 model achieved very strong results On the validation set, we reached precision of 92.92%, recall of 90.45%, MAP at IOU 0.5 of 96.43%, and MAP across thresholds of 83.87%. In terms of speed, our model can process around 95.8 frames per second, which is much faster than the real-time requirements of 30 frames per second. This shows that our system can be deployed in practical scenarios such as live surveillance. And now, the performance analysis. When we analyzed performance, we saw the most of the time was spent in inference, about 97% of total processing time. Pre-processing and post-processing together took only around 2.6%, which means our model is highly optimized for detection. We also tested the model of a model on over 1,000 images containing more than 1,200 gun instances. The results showed high precision, meaning very few false alarms, and high recalls, meaning most guns were successfully detected. The only remaining challenge were causes where guns were heavily occluded or partially visible. And if I come to the conclusion, our study demonstrated that YOLOv10 can deliver both high accuracy and real-time performance for gun detection. Our key contributions are achieving over 95 FPS while maintaining strong accuracy, demonstrating that gun detection can be both fast and reliable, showing that the system is suitable for real-world deployment. Practical application included automated 24 by 7 surveillance, rapid response systems, scalable deployments at the edge, and automated content moderation. And its limitation and future work included testing under extreme lighting or weather conditions, improving detection of partially hidden guns, extending the system of multiple weapon classes, and exploring adversarial robustness and multimodal sensor fusion. Overall, this work contributes a high performance solution for automated gun detection, which can help enhance public safety both in physical and digital environment. That concludes our presentation. Thank you for